to host Anat Levin in our seminar. So Anat is an associate professor at the Department of Electrical Engineering, the Technion. She received her PhD from the Hebrew University in 2006. During the years 2007 to 2009, she was a postdoc at MIT. And during 2009 to 2016, she was assistant associate professor at the Department of Computer Science and Applied Math at the Weizmann Institute. She is also a recipient of several prizes, like the Pammy Young Researcher Award, the Krill Prize from the World Foundation, the Bruno Memorial Award from the Rothschild Foundation, the Blavatnik Award, and probably I missed some. So Anat today will talk about a new approach she developed in computational imaging. So thank you, Anat, and welcome.
Okay. Thank you, Raja, for the introduction. Okay, so I'll talk today about rendering speckles in their statistics. So let's start by what are speckles. Okay, so speckles. So when you shine a laser through a scattering volume, like a piece of soap or a tissue, you get at the other end a bunch of speckles, like some random noise pattern. This is called speckles. And what happens here is that the scattering volume consists of particles with different refractive indices. And when the light hits a particle with a different refractive index, it scatters, it changes its path. It changes direction, and effectively there is an exponential number of paths that the light can pass through this volume. Each path has a different length, and therefore it has a different phase. Remember, this is a coherent illumination, and this phase is sum up on the sensor, and we end up summing random numbers with different phases. Sometimes they sum coherently, they interfere coherently, and then you get high intensity. Sometimes they interfere destructively, and then you get low intensity, and effectively you get some kind of noise pattern. Now, in many applications, speckles are indeed a disturbance because just noise. But they also have interesting statistical properties that people were trying to exploit in many applications, and we'll see some examples in this talk. And probably the most important property of speckle statistics is known as the memory effect, meaning that if you start to rotate the illumination direction, the speckles that you receive shift. Or a different way to say it, that the speckles that you receive from two nearby illumination directions are shifted correlated versions of each other. Now, it's a very, very important and useful property of speckles, and it has a lot of applications. And in this talk, you can go to the lab and measure speckles and start image speckle and start to measure their statistics. But the speckles that we have here are simulated, and this talk is on how to simulate speckles. And when I say simulate, I mean simulate them in a physically correct way, because if you just want to generate random noise, you can go home and you don't need to listen to this talk. I'm sure that you all know how to sample random noise. But we want not just to sample noise, but to sample noise that will have the statistics of real materials, of speckles resulting from real materials. Now, this property, which is called the memory effect, stating that speckles from nearby illumination directions are correlated. Now, it's valid for small illumination directions. I mean, if you tilt your illumination beam by 10 degrees, you'll see no correlation. But exactly how small or for what range it holds, it's a function of material parameters. Therefore, if we know how to simulate speckle statistics as a function of material parameters, then maybe we can also do the inverse process. When we measure speckle statistics in the lab, we can infer something and say what is a material. For example, it's well known that cancers change the scattering property of the tissue. So if we measure speckles from tissue, maybe we can detect cancer, maybe we can say what type of tissue, maybe we can say what percentage of vitamins and fat you have in a cup of milk. it has many applications. So there is really a lot of research about speckles and their statistics. And the research about it goes back maybe 4 decades ago to the invention of laser illumination. And it really has many applications in many fields, starting from medicine, biology, remote sensing, astronomy. In all these fields, you encounter speckles. And has a lot of applications. Maybe one interesting application that I'll just, to give you some motivation, let's just discuss. It's a paper by Katz and colleagues. And in this application, they're trying to infer, they're trying to see an object, for example, a fluorescent object behind a scattering volume, for example, fluorescent particles inside tissue. But the problem is that because they're deep inside the tissue, you don't see them directly, because the illuminations that emerge from this light source scatter on its way to your camera. And effectively, in your camera, you just see a bunch of speckles that carry no resemblance to the actual object. And this image just looks like noise, but remarkably, not noise. And from the statistics of this noise, you can actually go and recover your hidden object. And it really seems like a magic, but you can explain why it works, and it's really a very simple application of the memory effect. So this is just motivation for some amazing things that you can do with Speckle statistics and why we should bother to study them. So as we said, our goal in this work is to simulate speckles in a physically correct and efficient way. So before I'll talk about our approach, let's start by understanding what was the best way to simulate speckles before our work. So let's look at some scattering volume, for example, a piece of tissue, and let's zoom into some small window. And for simplicity, I'll do this analysis in flatland. So my volume will be a 2D volume, not a 3D volume, and my sensor will even be 1D. Okay, so now suppose that I know exactly where each particle is located, and I also know what is my illumination and where my 1D sensor is located. And then I can go and solve the wave equation, and I can compute the scattered field. Usually the field itself is complex. Usually with a camera, you only measure its intensity. And really, there are numerical solvers for the wave equation that you can go and download from the web. They're really, really accurate. But the problem is that, and also if you want to compute statistics, then you can look at another part of another window from the SOP. You have different particles, and then you get a different field. And you can look at another window and so on, and we get many different fields, and you collect statistics. So the main problem with solving the wave equation is that it's accurate, but it's terribly slow. And in practice, you can do with it maybe cubic volumes or volumes of a few dozen wavelengths or something like that. Now, another problem is that in order to solve the wave equation, you actually need to specify the exact location of every particle in the medium. Now, usually you don't have this information. And usually you also don't care, because, the particles can sometimes be even smaller than the wavelength. You're not going to see them. Then why should you care about their exact position? Usually what you care about is just some statistical description of the material. What's the density, what type of particles you have. And this is a leading approach in computer graphics. So in computer graphics, there is a very different way to simulate scattering, which is a few orders of magnitudes faster than solving the wave equations. And indeed, it takes as input just the density, just some statistical description of the material, not exact particle positions. And this is a family of Monte Carlo algorithms, maybe ray tracing. And as I said, ray tracing, Monte Carlo algorithms are very efficient, but originally they were developed for incoherent illumination, meaning that you don't get any wave interference from them. You just get smooth images like this one. And you can think of these smooth images as some low resolution version of some high resolution speckle pattern. So our goal in this work is to use ideas from Monte Carlo algorithms, from Monte Carlo tools, and use them to render speckles and to compute speckle statistics under coherent illumination. And so maybe it will be useful to start with. It will be useful to understand what is the relation between the output of a Monte Carlo process and the solution to the wave equation. So to understand this relation, let's do the following exercise. So suppose that we have some statistical description of a material, density, whatever, and we take this density, and from this density, we sample a few particle instantiations. All have the same density, but you have different particle position. And for each particle instantiation, you solve the wave equation, you get a scattered field, and you can also square it and compute the intensity. And then what we will do is we'll just average all these scattered fields. And when we average it, we get some smooth curve. And this smooth curve is the result of a Monte Carlo process. So definitely the Monte Carlo process, the intensity gives you some information about the scattered field. It gives you the expected intensity. But obviously there are no speckles here. So essentially, just the intensity, just the expected intensity doesn't give you enough information to reproduce all spectral statistics. So something is missing here. And the question is, what is missing? So now, let's do this exercise again. So again, we start with some particle position. We start with some density. We sample particle positions, and then we solve the wave equation. And but now, instead of just looking at the intensity, we look at the outer product of the scatter field with itself. So we take every pixel here and we multiply it by take every pixel from the signal and multiply it by every other pixel of the signal. And then we average this outer product over all the particle instantiations that we sampled. And we get essentially we get a covariance matrix. So again, every row in this covariance matrix is equivalent to pixel I multiplied by all other pixels in this field, averaged over multiple particle instantiations. So now, if you look at this covariance matrix, what you usually compute with a Monte Carlo ray tracing algorithm is just the diagonal of this matrix. But clearly, as you see, the off-diagonal elements of this matrix are not zero, meaning that there is more statistical information in the data, not just the intensity. So essentially, we are missing all these second-order statistics, all the off-diagonal elements of the covariance matrix. And our goal is to develop a Monte Carlo algorithm that can render the off-diagonal elements of the covariance matrix and not only the diagonal. Now, there is another type of second-order statistics which are still missing here, and this is a memory effect. So we didn't. So to see how the memory effect comes in, let's return to our synthetic exercise, and now let's add another illumination direction. So we mark the other illumination direction in green. It's not a different wavelength. It's just the OLED. The coherent illumination is the same wavelength, just a different way to plot it. Okay, so we take the other illumination direction, and we can also solve the wave equation given this illumination direction. And we get another field. We mark it here in green. Now, if we take a close look at the blue and green fields, we can see that they are correlated shifted versions of each other. And this is exactly the memory effect that we discussed. The memory effect states that if you tilt the illumination direction, you get shifted and highly correlated speckles. So now, again, we look at the green and blue fields, and we look at the outer product, and we compute a covariance matrix, which is, again, multiplying every pixel from the green signal by every pixel from the blue signal and averaging over all fields, over all the random fields that we have here. And again, we got a covariance matrix, and this covariance matrix has a strong diagonal. But if you note, now the diagonal is not in the center, but it shifted a bit, it's offsetted. And the reason that it's offsetted is, as we said, the blue and green fields are most similar after we do some shift, This is exactly the memory effect. Because due to the memory effect, because the blue and green fields are correlated after some shift, we see a strong correlation along some off-diagonal of the covariance matrix. Okay, so we saw two things about second-order statistics. So we said that in order to fully characterize Speckles, we need to compute the second-order statistics of the covariance matrix. So first of all, we need the second-order statistics between different pixels generated by the same illumination. But also, we need second-order statistics between speckles generated by different illumination directions. Okay, so we want to generate these covariance matrices, and the simple way to generate them is exactly what I described earlier. You sample many particle instantiations from a given distribution, you solve the wave equation, and then you do it multiple times, and you gather statistics, compute the covariance matrix. But this is terribly slow, because even solving the wave equation once is slow. And if you need to do it multiple times to collect statistics, there is just no way you can do it. So instead, our goal is to compute these covariance matrices with Monte Carlo algorithms. So maybe I'll start with a very quick review of what we do in standard Monte Carlo algorithms when we try to render intensity. And then we'll discuss what we need to change if we want to render covariance and not intensity. So in a standard Monte Carlo algorithm, we express the image as an integral over paths, all paths through the volume. And each such path has a throughput, which describes its contribution, or describes how much the energy changed along this path. And this throughput is a function of some material description, for example, the density, which is also known as the extinction coefficient, the albedo, how much it absorbs light, and the phase function. The phase function describes how much energy is, when a light hits a particle, how much energy is scattered to different directions. So given this statistical description, you can compute the throughput, and to compute the image, you need to average the throughput over multiple paths. And unfortunately, there is no closed form way there's no way to compute this integral in closed form. And what you need to do in order to compute it is to approximate it with samples. And you need to be a bit smart on how you sample paths. And this, in computer graphics, many efficient algorithms for this problem were developed. There's a family of what is called volumetric path tracing algorithms, which essentially use some sort of important sampling of paths. Okay, so this was about intensity rendering. Now, if we want to render covariance, so what we prove in the paper is that we can express the covariance as an integral of contributions over pairs of paths. So to explain it, let's add another illumination direction and another sensor. And we need to look at all pairs of paths from light 1 to view 1 and from light 2 to view 2. And every path has some contribution. Now, because we are dealing with a complex field, the contribution can be a complex number, not just a positive number, as in the case of intensity, and it has a phase. And the phase is basically proportional to the length of the path. And now, when we look at the contribution from a pair of paths, we just multiply the product of the contribution from path 1 and the product of the contribution from path 2. And that's again a complex number. And the phase is equivalent to the difference between the length of path 1 to the length of path 2. So for example, if the two paths are the same, and then the phase difference is 0, and then if the phase difference is 0, we get here a positive number. And in fact, so this is a positive real number. And In fact, this is exactly the same standard throughput that you get when you render intensity images. Okay, so we said that the covariance is essentially the integral of contributions over all pairs of paths that we can have in the volume. So now, in order to compute the covariance, we want to sample many random pairs of paths. And for each of them to compute the contribution, there is a simple formula for this contribution. We derive it in the paper. And compute the sample random paths, compute the contribution from for each path, and then average it over multiple paths. And then we have some approximation to the covariance. But the problem is that if you try to do it naively, it's just going to be very, very inefficient, because most of these paths are, if you just sample paths independently, most of these paths have no correlation between them, and they just contribute noise. And you can sample 1 trillion paths and you'll just get a noisy image. You won't conclude anything out of it. And as in standard Monte Carlo, we need to be smart about how we sample paths, so with some sort of important sampling. So to understand the problem, so remember that the contribution from a pair of paths is a complex number, which encodes the phase difference between the length of the two paths and also the attenuation along the amplitude attenuation along the path. So let's plot the contribution from a pair of paths in the complex plane. We said it's a complex number, we'll plot it in the complex plane. And now let's change one path. And now since we change the length of the path, we get a very different complex number. We'll plot it again in the complex plane. And if we choose a different path, we get yet another complex number and another complex number and so on. And so effectively, we get complex numbers with almost relatively random phases, and that's just because the path length, the length of the different paths can be very different, and then you get different phases. Now, when you average many complex numbers with different phases, usually you get 0, or at least some small number. So effectively, you have done all this work, you sampled all this path just in order to get 0, or to get some small number. So usually you just worked a lot and you'll just have a huge variance for this. So this seems like a waste. So let's try to do something else. Now let's look at a pair of paths that share all their nodes. So you see here that this pair of paths have the same set of nodes all the way, except of the segments connect them to the start and end nodes. And now, because these paths share the same nodes, they also have the same length. And if we say, if paths have the same length, we get here a positive real number. And now, if we just go and sample many pairs of paths that share all their nodes, we just get positive real numbers. And when we average such positive real numbers, we get some positive real number. And we get a meaningful contribution, not just 0. So essentially, and this is the most important observation of this work, is that in order to compute this covariance integral, we don't really need to look at all pairs of paths, but it's enough to look at pairs of paths that share all their nodes. This is a very important property because it really reduces the space of paths that we need to sample, and it makes the Monte Carlo, the rendering algorithm, much more efficient. Drastically reduce the variance that you get when you compute such an integral. Now, another useful thing is that the joint segment, you can just sample it in the same way that you sample it in standard Monte Carlo algorithms. And also it has the same complexity. And you know, in the Monte Carlo literature, a lot of smart algorithms have been developed. And we can essentially use all this wisdom and adapt it to our problem in render covariance matrices, because essentially we sample this path exactly in the same way that people have been sampling it when they compute intensities, when they do Monte Carlo for intensity rendering. So this is a very important observation that essentially you need to sample only paths that share all their nodes. Now, the argument that I gave here was relatively hand-wavy, and maybe some of you in the question box already typing questions on some mistakes I did and some things that I oversimplified. So I apologize for that. But I want to say that in the paper really justifies this mathematically, and we prove it, and the justification is much, much better than the justification that I just provided. Okay, so now that I told you that we have some Monte Carlo algorithm to render speckles, even to render speckle covariance, even if you didn't get all the details, I just want to show you the results. And what I do here is that I compare covariance matrices that we computed with our Monte Carlo algorithm with covariance matrices that were computed exactly with the exact wave solver. So here I have two covariance matrices when I have the same illumination directions. The two illumination directions are the same. I have another one when I tilted one illumination direction a bit, and I can tilt it even more. And you can again see the structure of the covariance matrices, that you have a strong diagonal which is shifted. And we say that this shift is a memory effect, because the field from the green illumination and the field from the blue illumination are correlated, shifted versions of each other. They're shifted. Now, another thing that you can see that the covariance that we got from the Monte Carlo algorithm agrees very, very accurately with the one that we got from the wave solver. The one from the Monte Carlo is slightly less noisy, but the Monte Carlo algorithm runs in a few minutes. Well, to get the covariance from the wave equation solver, we burned the huge cluster for a week. And also because of the limitation of the web solvers that we used, we did all of these comparisons only in flatland. But the Monte Carlo algorithm, we have no problem to run it in 3D. And for bigger scenes, the difference between these algorithms scales much faster. So the Monte Carlo algorithm is way more efficient, but still the take-home message that I want you to take from this slide is that the Monte Carlo algorithm is accurate, it's physically accurate, and it produces the exact same statistics that you get from an exact wave solver. Okay, so now we know how to render the covariance matrices, the second order statistics of speckles. Another thing that we can do if we know the covariance of the speckles is we can also sample speckle images. And we can do it as a function of material parameters. So for example, what we did here is we consider two types of phase function. In the first row, we have an isotropic phase function. Isotropic phase function means that the incident illumination scatters equally in all directions. And in the second row, we have a forward scattering phase function, meaning that when a light beams a particle, it scatters, but still most of the light is going forward, and only a small percent is scattered in the backward directions. And forward scattering phase function are interesting because that's what happens in tissue. Tissue usually have a very forward scattering phase function. Therefore, for tissue imaging applications, that's the more interesting case. Now, we sampled here speckle images from a few illumination directions. And you can really see that this is not just noise, but you can see it's a noise which satisfies the memory effect. You can see how the speckle patterns shift from different illumination directions. Now, I already mentioned at the beginning of the talk, and it's very well known in the optics literature that the memory effect usually holds for relatively small angles. And the exact dependence or the exact decay of the correlation with a function of angle depends on material parameters. It's different for the memory effect is different for different materials. And we can really see it in this example. For example, in the first row, you can see that in the first image, the speckle pattern already changed a bit. But in the second case, for a forward scattering phase function, the correlation holds even for this wide illumination angle. Now, an interesting question in the optics literature and also for many scientific applications, is how the memory effect, how the correlation decays is a function of angle. Because as I told you, the decay as a function of angle is different for different materials. So if we know how it decays as a function of angle, we can distinguish between different materials from the speckle that generate. So the way to compute it is just we take one speckle image and we correlate it with itself. So usually if you correlate a speckle pattern with itself, you just get some impulse. I mean, for zero displacement, you get a strong correlation. For every other shift, you get zero correlation. Then we just take this peak value and you plug it as the first point in a curve. And now let's take the first image and correlate it with the second image. So now the correlation looks like it again has a strong correlation peak, but the peak shifted a bit from the center because there is some shift between this image and this one. And also the peak is slightly weaker now because the correlation is not perfect. And if we'll correlate the first image with the third one, then the shift is even bigger and the value of the correlation is even lower because the correlation is not perfect. So again, we take this value and we plug it in our curve and we repeat it for different angles and we get such a curve, which describes, this curve essentially describes how the correlation decays as a function of the angle theta between the illumination directions. Now, as I said, computing this curve is very important for many scientific applications. And because it's such an important question, it has many practical implications. And because there is no up to this before this work, there was no good way to evaluate it to compute this. There was no good way to compute this decay numerically. Then what people usually do is just go to the lab and measure these curves because it's so important. And you can really find papers where the main contribution of the paper is that, like, we went to the lab, it's a lot of work, we measured memory effect for different types of material, for different thicknesses, and we report various statistics for some materials of interest. But with our work, we can do all of this numerically and save all this work. Now, I should say that in the optics literature, there is one analytical result which describes how the speckle correlation decays as a function of angle, but it's based on what is known as the diffusion approximation. And the diffusion approximation is an approximation, and basically it's valid when the scattering layer is very thick, so that particles scatter multiple times, and eventually when the light scatters multiple times, and by the time it comes out of the tissue, it has no angular information. So under this assumption, you can derive an analytical result, but it's well known in the literature that this approximation is correct. It's not correct for every type of material, and in practice, people have noticed in the labs that for many practical materials, the memory effect is much wider than what is predicted by this pessimistic curve, by this analytical result. But currently, the only way to validate it is actually to measure in the lab. But if our numerical solver, with our algorithm, we can go and analytically compute the decay of the memory effect. We can do it very efficiently for any type of material, for any material parameters that we want. And for example, here we show the memory effect as a function of the phase function. And we can see that when the phase function is isotropic, then it really agrees perfectly well with the theory, with the diffusion approximation. And that's just another way to validate that the results that we get here are accurate, that it's not just that we didn't make too many approximations. But for other more forward scattering phase function, you can see that the decay of this curve is much slower, or say differently, the memory effect is much wider. The memory effect correlation holds for much wider angles. Okay, so we're in the paper, so we can do it very efficiently. And in the paper, we provide such curves for different types of material parameters and whatever. Now, I already mentioned this application in the beginning of the talk. That's a very interesting application of the memory effect in order to see through scattering material. So suppose you have a set of incoherent illumination source behind the scattering material, for example, fluorescent particles inside tissue. And since you cannot see them directly, what your camera observes is just a bunch of speckles. And the image looks just as random noise. But amazingly, if you look at the autocorrelation of this noise, then it's just equivalent to the autocorrelation of the latent image. And from this autocorrelation, you can apply iterative phase retrieval algorithms and reconstruct the underlying object. So this is really an amazing algorithm. I think it's a beautiful usage of the memory effect. But applying it in practice involves some challenge. And part of what we were hoping to do with our simulation is to better understand when this algorithm is working and when it's not working. So you don't just need to go to the lab and try and see if it's working or not. And basically, this algorithm has a few issues that limit this algorithm. One such issue is that usually the extent of the range of the object that it can recover, it's relatively small because it relies on the memory effect. And as we said, memory effect usually holds for relatively small angles. And therefore, the object, since the object should be included inside the memory effect range, we can usually recover relatively small objects. Now, another issue which is not well discussed, but it's also a very serious issue, that it can recover a relatively sparse, a relatively small set of independent illumination sources. Because as you add more and more incoherent illumination sources behind your scattering medium, I mean, as you add more red points on this object, the contrast of your speckle image decay. And effectively, eventually, if you add many of them, then what you'll see here is just a smooth image. So as I said, part of what we try to do in this work is to understand the limitations of these algorithms and also suggest some ways to overcome them. Now, maybe I'll say that another issue, which I think is a very serious issue, is that usually the way that experimental realizations of this idea were done earlier, usually the light source is in the far field of the scattering medium, or at least the light source is a few centimeters behind the scattering medium. But one of the more interesting applications of this idea is to actually detect fluorescent particles inside the tissue and not a few centimeters behind the scattering medium. And the question is why all the successful experimental realizations of this idea consider light sources behind scattering tissue, not inside it. So my understanding is that the statistics of speckles that you get from far field sources and from near field sources, far field, I mean that they are far behind the source, and near field that they are inside the scattering medium. So my understanding is the statistics of far field and near field speckles are not the same. And for far field, it's a bit easier to understand what's going on because we have some analytical results based on the, for example, they show you this diffusion approximation, but in the memory effect, it's a bit harder to understand what's going on. And what we are hoping to do is also to be able to render the statistics in the near field. And therefore, maybe we'll understand new things about correlation in the near field, and we'll be able to say something, be able to adapt this amazing algorithm to work also in the near field. So I'll say that, okay, maybe I skipped this earlier, but the rendering algorithm that I described earlier, it assumes that the illumination source is in the far field, that you illuminate the sample, but by a collimated beam by a directional source. Now, to change it and render speckles in the near field, it's not complicated conceptually. All you need to do is to do a Fourier transform on your speckles. But despite the fact that it's conceptually simple, doing it in practice, translating it to a computational algorithm actually involves some challenge. And we have a new upcoming paper on how to, it will be presented in SIGGRAPH Asia in a few months, on how to render statistics of speckles in the near field. But now, given this new tool, what we hope to do is to understand how speckles in the near field differ than speckles in the far field, why it's harder to do it in the near field, and hopefully, indeed, to be able to apply it to this important application of detecting fluorescent particles deep inside the scattering tissue. Okay, so I'll just summarize that we spoke today about the problem of simulating coherent speckles, coherent scattering, and we formulated the Speckle covariance as an integral in path space. And we suggested an efficient algorithm for computing the Speckle covariance using Monte Carlo algorithm. And we saw that this algorithm is really physically accurate. It agrees very, very accurately with statistics that were computed with the exact wave solvers, but yet it's a few order of magnitude more efficient. And also we showed that we can use it to compute some interesting properties of speckles, for example, the decay of the memory effect. And we hope that we can use it to potentially improve many computational imaging applications that actually rely on speckle statistics. So before I conclude this talk, I just want to say that if you want to use the simulator, we have a code online. You can take a picture of this URL, and I'll be very happy if you use it. And if you send us, please send us. Feel free to send us questions and feedback. We really appreciate it. Okay, so I'll stop here, and maybe we can have some discussion. Let me see what we have in the question and answer tab.
So thank you very much, Anat. So we have several questions. So the first question is from Jenison. So it is, can this MC algorithm be applied to study the scattering from radar targets using MM wave divided by EM waves? If yes, what suitable modification need to be done other than solving the EM wave equations?
Yeah, so my guess is that yes, but I should say that I don't understand enough about radars to answer this question. My guess is that the same ideas can be applied, but I'm not sufficiently familiar with all the math. I'm sorry.
Okay. So the second question is, when sampling paths, you mentioned that you only need to sample path pairs that share the same nodes, so that the difference in path lengths is a real number. Why not consider the path lengths whose difference is a complex number? Would the complex component give you any additional information? Okay,
so the answer for this, and I said that I cheated a bit in my explanation, I admit, and it was oversimplified. And yes, we do sample such paths. And if I go back to this slide, effectively, the contribution is not always really real number. What happens that the contribution from the joint segment is a real number, but you also have all these 4 segments, and the length of these 4 segments is not the same. And from this, you do get complex values, and effectively, the correlation that you get is a complex number. It's not a real number, but it's still the same idea that yeah, you do get complex numbers, but they all have the same phase. So, I mean, I'm happy that I got this question, because it means that you keep track and you don't let me cheat you. But I mean, my explanation was oversimplified.
Thank you. Another question by Varun Kelkar. Why do large tilts have curved diagonals in the covariant matrices?
Okay, so that's a good question. And the answer is that this covariance matrix is plotted as a function of theta. I mean, the axis here is angle theta. And if you want to make it a straight curve, you need the axis need to be sinus theta and not theta. It's a simple change which can be applied. But usually the memory effect depends on the difference between sinus, the difference between the sinus of angle 1 and the sinus of angle 1 and the difference of sinus angle 1 and sinus angle 2. And here we plot it not as a function of the sinus of the angle, but as a function of the angle. And I forgot what are the exact axes here, but the angles here are large. Maybe it even gets to 40 degrees or something. And in this range, you already have a difference between theta and sinus theta.
Okay, thank you. Another question. What phase retrieval algorithms do you use and how are they employed?
Yeah, so when I said about phase retrieval, it's not really, okay. So the result that I showed here is just an application of the algorithm of Katz et al. It's not really part of our algorithm. So here we just use the standard finite algorithm. You can use many smarter phase retrieval algorithms. I mean, we played a bit with some of them. You can get slightly better results. But I mean, the phase retrieval only comes in as part of the application. It's not really for the actual rendering algorithm.
Okay.
You can use many various phase retrieval algorithms.
Yeah. So another question, and I am not sure what is meant here. There is the evanescent imaging like TIRF for near-field speckle characterization.
Yeah, so I'm also not sure that I understand the question.
So if the person that wrote the question can write it again, I think it will be helpful. Another question is, what wave function algorithm did you use to compare with your MC method?
We use something which is called the MuDiff. It's a wave solver that we download from the web. It's using what's called the integral. I have the reference here. Just let me find it. It's relying on what's called the integral equation, the integral formulation of the wave equation. There is also a differential version of the wave equation solver. Of the wave equation, it's using an integral formulation of the wave equation. It's called MuDiff.
Okay. And another question is, how these Speckle statistics affect the tissue optical properties like refractive index?
Well, they take as input the refractive index. I mean, what our rendering algorithm gets as input is a phase function. And the phase function, way to compute the phase function depends on the refractive index variation, the size of the particle, the refractive index inside and outside the particle. And from that, you can use mean theory and compute the phase function, and that's an input to our algorithm. I'm not sure that this answers the question, but if not, please clarify the question.
Okay, so if the question was not answered, so please rewrite it. The first question was written again. TIRF is total internal reflection fluorescence, and this question was just a suggestion of how to do near-field speckle characterization.
And I'm still not sure that I understand it. I mean, you can do a near-field characterization by solving the wave equation. We wanted to do it with Monte Carlo. It's not terribly complicated. Just we need, from the Monte Carlo viewpoint, we needed to employ a bunch of tricks in order to get the Monte Carlo to converge. Yeah, I guess that we don't fully understand each other. Sorry.
Okay, so I think we have no more questions.
Okay, so thanks you all for listening and participating. And if I didn't answer all the questions, please feel free to send me a personal email, and I'm happy to keep the discussion. And thank you a lot for inviting me to this session.
Yeah, so, okay, so there is another question. I want to ask that while calculating the tissue optical properties, how these Speckle statistics, not sure if it, how these Speckle statistics help.
Yeah, so again, I'm not sure if I fully understand, but Speckle statistics, for example, you can compute the optical depth, you can compute the optical depth of the material, you can compute well, when an incident beam gets in, by how much it scatters, when it comes out, how much it scatters. And you can compute how the memory effect change. Maybe the question is the other thing. Suppose that you know, I mean, if you give me some statistical description of the tissue, for example, the type of particles, their density, whatever, and I compute the Speckle statistics, then I can also do, I mean, I hope to be able to do in the future work to do the inverse process. I mean, go to the lab, measure Speckle statistics, measure how quickly the memory effect decay, and then find some tissue parameters such that the statistics predicted by these tissue parameters matches the statistics that I measured in the lab. And then I can invert from the Speckle statistics that I measure in the lab, I can invert the process and estimate something about the tissue, about the type of tissue that I have and its optical properties.
Okay, so thank you very much, Anat. This was a very interesting talk. And I believe that it will have a lot of follow-up. And I remind everyone that this talk is part of a series, and we have every 2 weeks talks with great speakers like Anat in the space seminar. So you are welcome to look at the website. Thank you very much.
Thanks a lot.